So someone has closed the door, so I think this is meant to be a sign that we should start. So welcome to the tutorial on text quantification. I am Fabrizio Sebastiani from, well, a local, from the Qatar Computing Research Institute. And the tutorial I will give today concerns a task, quantification, that has recently gained attention and that, say, I foresee will gather attention more and more. So, I mean, while many of you probably have never heard of quantification, but I guess that when we start talking about it, you will some of you might realize that has done some research in quantification or used quantification without knowing it. And it's actually a task which has, it's not of exclusive interest to NLP, computational linguistics, or text, but has several applications in various fields, including, we'll see, applications to machine learning, within data mining, within statistics, plus several other applied fields, such as social sciences or epidemiology or the like. Well, before starting, I would first of all urge you to download the most recent versions of these slides at this address that you see here, and I'll actually try to read it out. It's bit.ly/1Q capital F G capital T Y Z. Okay. I mean, the slides that you can download here are slightly updated from the ones that for whose you have a printout. Anyway, so what is actually quantification? Before giving you a formal definition, I've tried to come up with this graph. Some of you might have seen this before. This was a study. This is from a paper by Peter Dodds and a group of other American social scientists, which appeared in 2011, and which attempted to measure happiness in the US by analyzing tweets. Okay, so this essentially was an exercise of what we would call sentiment classification of tweets. Okay, so what these people did, well, they got access to the Twitter firehose. They downloaded tweets that originated in the US, and they tried to do a sort of sentiment classification for tweets that displayed either happiness or unhappiness. And they tried to gather some interesting statistics having to do, with groups broken down by, say, state within the United States, and some interesting statistics having to do with temporal patterns. Okay. So this display shows that essentially, on the y-axis you have happiness, okay, from 0 to 1, and this shows that actually more happiness was recorded first of all on, say, Fridays, say when people go out to have a drink in the evening, while unhappiness was mostly recorded on Mondays, for instance. Okay, so actually, the Mondays are the light blue dots, while the Fridays are the red dots. And, peaks of happiness were recorded on Christmas Day, on New Year's Eve, Valentine's Day, the Royal Wedding Day, etc. While peaks of unhappiness were recorded when Amy Winehouse died, on the day of the Japan earthquake, the London riots, etc. So, some statistics, some of these unsurprising, some of these fairly interesting, were actually gathered. Okay. So, as I said, these people actually applied a form of sentiment classification on Twitter. But what I would actually argue is that these people didn't do sentiment classification. They did sentiment quantification. So these people were not interested in whether an individual tweet displayed happiness or unhappiness. They were interested in figuring out the frequency of tweets displaying happiness. They were interested in figuring out the percentage of tweets that displayed happiness and to record them on a time scale. Okay. So in a sense, I mean, they were interested not in classification at the individual level, but they were interested in classification analyzed at the aggregate level. Okay, so essentially with the goal of detecting class percentages. So this is another example. This is from the, let's say, a couple of years ago, I mean, when in Italy we had political elections, okay? And when there are political elections, most news portals, I mean, come up with graphs like this, in which, let's say, positive mentions and negative mentions of the different candidates are recorded on a time scale. Okay, so, I mean, for instance, we have a fairly colorful politician called Silvio Berlusconi, and he got a peak of negative mention on February 2 because, I mean, he had come up with some outrageous statement. Okay, so again, here, I mean, people are trying to display, let's say, plots about positivity and negativity within tweets, with the goal not of analyzing individual tweets, but in figuring out percentages, figuring out class prevalences. Okay, so with the goal of actually doing some aggregate analysis. So, I mean, this pattern can be recorded in several different fields. So we all know classification. Okay, so classification is ubiquitous. It's a ubiquitous enabling technology which finds applications in several different fields. But in many such applications, the real goal of the classification is not determining which class the individual item belongs to, but it's determining the relative frequency of each class in the unlabeled data. And this task has recently been called quantification. It goes under different names in different fields. We'll look at it. But, I mean, these are some examples. Okay, so say among the blog posts concerning the next presidential elections, what is the percentage of pro-Democrat posts? Among the reviews of the Kindle Fire posted on Amazon, what is the percentage of 5-star reviews? And above all, I mean, how do these percentages evolve with time? So, I mean, for instance, I mean, the reviews of the Kindle Fire might evolve, I mean, towards the better or the worse, depending on whether, say, the price of the Kindle Fire has been cut in half, okay? So, I mean, the reviews will go up. And so this will allow, say, Amazon, I mean, to monitor whether it's, let's say, cutting in half the price has had beneficial impact on opinions about the Kindle Fire. So, I mean, the first example is actually binary quantification, because, I mean, we have pro-Democrat and pro-Republican posts. Okay, so, I mean, essentially we have two classes. The second example, I mean, 5-star reviews, it's probably a type of ordinal quantification in that we have 5 different classes, 1 star, 2 stars, 3 stars, and these classes are ordered. Okay? So, I mean, there are various variants of quantification, and we will actually touch on them during this tutorial. This task has, as I said before, I mean, has several applications, and the fields where this has been applied are, say, IR, information retrieval, machine learning, data mining, NLP, not to count, I mean, other more applied tasks, such as I said, I mean, social sciences, epidemiology, etc. Quantification, actually, it's a notion that applies to any kind of classification, not just text, but, I mean, you could classify and quantify horses or stars. But we will, I mean, we are in an NLP conference here, so we will mostly be interested in text quantification of different types. So this is sort of the outline of the tutorial I will give today. I will introduce a few fundamental notions having to do with quantification. And then I want to try to whet your appetite by actually looking through a few applications of quantification in these various fields. The third part, it's going to be a fairly brief part, which has to do with the evaluation measures of quantification. And as you might imagine, the evaluation measures are pretty different from the ones that we actually use normally for classification, such as F1 or the like. Probably the core part of the tutorial will be part 4, in which I will look at supervised learning methods for doing quantification. So if time allows, I mean, I will look through briefly to some advanced topics. So let me introduce the notion. I will, in this introduction, I will essentially go through 2 or 3 fundamental notions, such as the notion of distribution drift, and I will discuss why quantification is a bit paradoxical in some sense. So, first of all, I mean, quantification is a variant of classification. So, is here everyone familiar with classification? Should I go through, I mean, some essentials of classification, or do we all know classification? So who doesn't know classification and would like to see a couple of slides about it? Oh, okay, so I'll skip the primer on classification. And I will, let me say, I mean, that quantification, as I've discussed it up to now, it tends to go under different names in different fields. Okay, so the first field where it originated was actually statistics, and especially its application to epidemiology. We will see a few of them. And in this field, especially medicine and epidemiology, this goes under the name of prevalence estimation. So class prevalence is what we tend to call class frequency. Okay, so the percentage of items that belong to a certain class. While machine learning is an area which has taken up the notion of quantification a bit later than statistics, and within this discipline, quantification goes under the name of class prior estimation. Okay, and the third, I mean, the third discipline, main discipline, is data mining and text mining and IR, where actually the discipline was called quantification, and the name has sort of stuck. Okay, so this is the typical name by which it goes today. Okay, so I mean, throughout this tutorial, you will see several terms which are actually synonyms. Okay, so relative frequency of a class, the prevalence of a class, the a priori probability of the class, or simply prior probability. Okay, so these are all synonyms for the same thing. There are sort of slight differences among the 3 fields I've mentioned, in the sense that, we will see that in epidemiology, epidemiology in particular, this is an area in which quantification is done without actually training data. Okay, so essentially we have no classifiers there, but we have what epidemiologists and doctors call screening tests. Okay, so medical tests for assessing whether a patient has an illness or not. And we will see that these are a bit akin to classifiers. And a second difference is that quantification as a task is a task of independent interest in the first and the third field, okay, statistics and data mining, while in machine learning, it doesn't have independent interest, but is actually performed only with the goal of improving classification accuracy. So it's, in a sense, ancillary to classification. You might have realized, okay, by my presentation of this, that quantification may also be defined as the task of approximating a true distribution, okay, approximating a true distribution across different classes by means of a predicted distribution. So here we have a histogram where the blue bars actually display the percentages. Okay, so take, say, a set of product reviews. Okay, so they are distributed across very negative, negative, neutral, positive, and very positive. Okay, so the blue bars actually here represent the true distribution. Okay, so the kind of distribution of the product reviews across these classes that would be measured if we had a reliable human annotator annotating all of these reviews, or if we simply take the, say, stars which have been attributed by the authors. While the red bars actually represent a predicted distribution, so the one that a classifier might, or a quantifier might come up with. And of course, I mean, quantification essentially is the task of approximating as well as possible a true distribution via predicted distribution. Here, this specific histogram is actually a case of ordinal quantification because the 5 classes are ordered, but you might have, say, green, yellow, and violet. So, I mean, 3 unrelated classes. And in this case, I mean, we would have traditional, simple, single label, multi-class quantification. So, the very notion of quantification is interesting because of what machine learning people call distribution drift. Okay? So you may have heard of concept drift. So concept drift is the, within machine learning, is the phenomenon according to which the test data or the data on which you actually apply your classifier tend to exhibit some significant statistical difference from the training data. Okay, so it's essentially a case in which the IID assumption breaks down. Okay. So I mean, standard machine learning algorithms in general are based on the so-called IID assumption, which means that we assume that the training, both the training and the test data, are sampled identically in a way which is independently and identically distributed. Okay, so I mean are sampled randomly from the underlying distribution. So actually it means that since this is the underlying assumption, okay, that underlies, I mean, supervised learning, when this assumption breaks down, well, suboptimal classification accuracy and quantification accuracy may derive, okay? Simply because, I mean, the test data are different, okay? So, I mean, this drift may derive from different reasons, okay? And here, when I'm talking about distribution drift, it's a sort of a special type of concept drift, okay? It's a type of concept drift in which it's essentially the class prevalence, the class frequency that is different in the test set and in the training set. So I'll give you, I mean, a very easy example, okay? So take September 11, okay? So if you looked, say, at a backlog of news from 2001, you would probably notice, I mean, that, let's say, the news items having to do with class terrorism were radically different in August and in September, okay? Because, I mean, after September 11, a lot of news items had to do with terrorism. Okay, so you would witness the fact that if you train for class terrorism on August data and test on September data, your accuracy would be suboptimal, okay? Because the class prevalence on August data is radically different from the class prevalence in September data. So this is what we call distribution drift. And distribution drift may derive from several reasons, okay? So one problem is that the environment is not stationary across time and across space and across other variables, okay? So essentially the testing conditions are not reproducible at training time. So I mean, this is the terrorism example, okay? Another problem is that the process of labeling training data is sometimes class dependent, okay? So I mean, suppose that we want to come up with a classifier for classifying medical reports, and we are interested in figuring out which medical reports are about a certain rare illness, okay? So typically, if we take a random sample of medical reports, very few such reports would be positive examples, okay? So, I mean, if we want to train a reasonably accurate classifier, we would undersample the negative class, okay? So we would remove a lot of negative examples and try to get a very high number of positive examples, okay? So in doing this, it's clear that the class prevalence that we build into the training data is radically different from the class prevalence that occurs naturally in the testing data, okay? So, I mean, this is what we call stratified training sets. And the third reason is that the labeling process may introduce bias in the training set. So suppose we use active learning, okay? So suppose we use active learning in order to increase the training set. Well, active learning tends to identify items which tend to be highly useful in the training process. So it's typically the case that active learning would come up with examples that tend to be positive, that tend to be in the positive class rather than in the negative class. So it's quite likely the case that if active learning has taken part in the labeling process, then the positive class is overrepresented with respect to the negative class. Okay, so because of all of these reasons, I mean, the kind of class prevalences that we find in the training set might be significantly different from the ones that we find in the test set. So, I mean, as I said, distribution drift is one type of concept drift, okay? So machine learning people tend to distinguish concept drift into 3 different classes, okay? So 3 different types, 3 different cases, okay? So one case is the case in which the class priors, okay, may change, the class prevalence. And this is the one we are interested in. The second one is when the class conditional probabilities change, okay? So the probability of, let's say, of X belonging to class, let's say, the probability of document or item X given class Cj. And the third is the one in which the posterior distribution changes. So this is actually the scores that, say, a probabilistic classifier comes up, okay? So the probability that a given document X has class Cj. And of all these cases, it's essentially the first that we are going to be interested in here, and the one that poses problems for quantification. So I said that quantification has an inherent paradox, okay? So the paradox is this, okay? So typically, the typical way, I mean, we would solve quantification is by a strategy which we call classify and count, okay? So if we want to do quantification on tweets, we do sentiment classification on all of the tweets. We count the ones which have received a positive class, and that's our class prevalence. That's our estimated class prevalence. Well, if we have a perfect classifier, it's also, a fortiori, a perfect quantifier. That's clear, okay? But if we have a good classifier, it's not really clear that this is going to be a good quantifier either, okay? And this is an example, okay? So take classifier A. Classifier A applied to a given test set returns 18 false positives and 20 false negatives, while classifier B returns 20 false positives and 20 false negatives. So which classifier is better? Well, A is certainly better because it returns a smaller number of examples. But in terms of quantification accuracy, actually we should prefer classifier B, because classifier B, by the fact that it makes an equal number of false positives and false negatives, is a perfect quantifier, okay? Because false positives and false negatives cancel each other out when it comes to computing class prevalences, okay? So it's a bit paradoxical that a classifier with a smaller classification accuracy can have higher quantification accuracy, okay? So, in a sense, I mean, I want to leave this paradox open, but to me, this means that, at the very least, that quantification should be studied as a task in its own right and not simply be considered as a byproduct of classification. So let me go through some historical development, okay, so which will allow us to see in which application fields, I mean, quantification has been found to be of interest. The very first case was where quantification methods are recorded. It is actually the case of epidemiology. In epidemiology, well, you know that epidemiologists is that branch of medicine which is concerned with aggregate, aggregate data. So epidemiologists are not concerned on whether I have cancer or not. They are concerned on how many people have cancer from a certain population, from a certain age group, etc. Okay. So epidemiologists often rely on so-called screening tests. Screening test is a sort of a medical test that a patient like I undergoes in order to check whether I have cancer or not. Unfortunately, I mean, these kind of tests are imperfect. Okay, so sometimes I get diagnosed with cancer while it is not true that I have cancer. So I am a false positive. Sometimes I am diagnosed to be free of cancer, while instead I have cancer. Okay, so that's a false negative. Okay, so an epidemiologist, who applies a sort of screening test on a population of 1 million patients, okay, will draw some statistics about how many people have cancer. Okay, but the problem is that these statistics may be biased, okay, by the false positives and the false negatives of the test. So a screening test, is a bit like a classifier, okay, because it can have true positives, true negatives, false positives, and false negatives. The difference is that typically a screening test has known precision and known recall. Okay, so it has fairly constant precision and recall. Okay, so this can be the kind of its quantification accuracy can be obtained by, let's say, extracting classification data, counting, classifying and counting, and then correcting for its known sensitivity, its known recall and known precision, in a way that I will specify later. And the first method to correct for known precision and known recall was indeed proposed by these guys, Gart and Bock. This fact of trying to quantify by screening tests is still an active field within epidemiology. So, there is sort of a second stage of quantification research, and this is a stage in which actually machine learning people started to get interested in this. And I here speak of different stages because these three different fields, okay, data mining, machine learning, and statistics, epidemiology, sort of discovered and rediscovered the same methods all over again, without being terribly aware of each other. Okay. So in machine learning, people started to get interested in what they call the estimation of class priors, because the goal was that of building classifiers that are robust to the presence of distribution drift. Okay, so that classifiers that can behave well when the IID assumption breaks down. Okay, so when class priors change from training and test. Okay, so methods where the classifiers that are trained on the training data can be corrected, can be attuned to the new characteristics of the data. And here, the first methods, okay, to be developed within machine learning were at the beginning of the year 2000, with the paper of Marco Serens and colleagues being probably the most influential. And this is still an active area of research within machine learning. The third stage is when data mining people discovered quantification, and they discovered quantification as a task in its own right, not just as a task functional to producing better classifiers, but because, in data mining and in text mining, etc., there are indeed applications where we want to simply to estimate class frequencies, and sentiment classification in tweets is one such case. And there is a single researcher, which is George Foreman from Hewlett-Packard Labs, which is probably responsible for starting out the interest in quantification within data mining. And it's indeed, the applications in data mining that have sparked the most recent wave of research in quantification. I've already told you about screening tests and prevalence estimation, so let me skip to the next one. Okay. So, what I want to actually, yes? Sure.
So in machine learning, actually, in genetic models, we care about the class priors. So you're saying that this one is only applicable to genetic models? And not only
to genetic?
Genetic models, like Bayesian models.
No, there are several. There are several learning algorithms. Okay, so there are several algorithms where the class priors influence your decision. Okay, so I would say that all of the methods that estimate posterior probabilities are influenced by the priors. Okay, so if the priors change, okay, then your posterior estimate, your posterior probabilities change, and when you have to argmax over them, okay, so your choice might be different. Okay, so the The most evident examples would be Bayesian, say, naive Bayesian classifiers, etc., but probably there are several others. Okay. Yeah, I was going to say that quantification has several related tasks. Okay, so I mean, some of you might have come up and say, "Hey, this looks like density estimation in traditional statistics." Yes, I mean, density estimation is similar in the sense that, well, I mean, say a typical textbook case from density estimation. So you have a large urn containing a lot of white balls and black balls. Okay, so you have to estimate the percentage of white balls. Okay, so I mean, this is similar, but there are two key differences. Okay, so first of all, in density estimation, you assume that you cannot actually examine each individual item. Okay, so I mean, with the white balls and black balls, certainly you don't want to pick them all and check whether they are white or black. Okay, so essentially what you want to do is sample the urn, okay, and try to estimate a class prevalence from your sample. Okay, so this is not the case in say in text quantification when you do tweet quantification, for the simple case that tweets are digital objects and checking them all is not a problem. Okay, so it can be done by computer. Okay. The second difference is that in density estimation, say with the white and black balls, so you assume that for each individual item, you can deterministically check whether the item belongs to the class or not. Okay, so you pick a ball and you can, with certainty equal to 1, you can determine whether it's white or black. This is not the case, say, in sentiment quantification, because, I mean, classification typically has a degree of subjectivity. Okay, so your decisions are uncertain. So, I mean, density estimation and quantification have points in common, but have differences. And these kind of differences tell us that quantification is related to classification, okay, because we have subjectivity, and because in classification we can classify each individual item without any problem. So a second area which is related is the area of so-called collective classification. Collective classification is, say, when we want to classify networked items, such as, say, hypertextual pages, web pages. Okay. So in collective classification, we typically want to use features such as text and links, okay, so endogenous and exogenous features. Okay. But collective classification is different in the sense that even if, I mean, well, I mean, it's different for two reasons. Okay. So first of all, in collective classification, we assume the existence of explicit binary relationship between items, which is not true in quantification. And second, in collective classification, we are interested in the classification of individual items, while quantification, we are only interested at the aggregate level, as I said. So, I mean, let me try to enter now in the more technical part, just a little notation and terminology. So, we will be interested with the domain calligraphic X of items, and which we may think of as, say, textual documents, and a set C of classes. And as I see, I mean, we will be interested in different brands of classification, different brands of, say, quantification equivalents. Okay? So the first brand is certainly binary classification, where each item has exactly one of two classes that make up C. Single label multi-class classification is when each item has exactly one of a set of classes with n higher than 2. While multi-label, multi-class classification, each item may have 0, 1, or actually several among a number of classes n with n higher than 1. Okay. So, I mean, these are the standard types of classification, and each of them has a quantification equivalent that we will be interested in. A slightly more exoteric type of classification is ordinal classification, which is also called ordinal regression. And this is when the n classes are ordered, such as when we have product reviews classified as 1 star, 2 stars, 4 stars, 5 stars. Okay. We will not actually deal with the metric regression case, I mean, which is when items have a sort of a real number as a label. Okay, but there are sort of applications like this too. So, I mean, for each such brand of classification, we will be interested in figuring out which methods can we use to solve its quantification equivalent. So, in terms of notation, we will use sort of standard notation from probability theory. So, we will have boldface X to represent the vector, I mean, that represents the vector of features that represent a certain item. C represents a set of classes. And by PSCJ, we will represent the true class prior of class CJ in a set S. While by het PSCJ, we will represent our estimation, okay, so the estimation of the class prevalence. Here, hat P with sup M will represent the estimation that we obtain via method M. And by these other notations, I mean, we will represent, I mean, this is a fairly common notation, I mean, for representing posterior probability of CJ returned by the classifier. So that's the confidence score that the classifier returns in the fact that X belongs to class CJ, while P delta J, to us, I mean, we represent the probability that a positive decision for class J has been returned for the document. Okay, so the probability that binary classifier for class CJ, or the classifier actually decides that the document is in class CJ. Okay, and here, I mean, the fraction of items that are labeled as CJ by the classifier. But anyway, I mean, I'll try to work across the various formula with you. So let me go a few applications where classification has been put. First of all, I mean, you will pretty much notice that these classifications, these applications are actually various dimensions of classification and dimensions of quantification are actually represented. So, I mean, in classification, typically we have classification by topic, but also have classification by sentiment, or say, classification by language, when, say, classification by language is when we do language identification. And for all of these dimensions, I mean, there are indeed quantification equivalents. So we will see cases of application of quantification by topic in the social sciences, in epidemiology, etc. Quantification by sentiment is, I claim, something ubiquitous. Okay, so I urge you to think of applications where you have looked at sentiment classification of tweets, and I think that 99% of those applications are actually quantification. Okay, because when you deal with tweets, okay, you are really hardly interested in what the individual Twitter user, okay, expresses. Okay, so you are normally interested in trying to gather class preferences and aggregate statistics. Okay, so 99% of what we see in tweet classification today is actually tweet quantification. And I mean, quantification by language is essentially something like estimating language diversity or the like. So, and in general, I mean, when you see applications of quantification in the literature, there are some, say, proper applications of quantification. So it's, I mean, a researcher that is aware of the fact that quantification is different from classification and applies a true quantification method. But there are some, many other applications where people do quantification without knowingly doing so. Okay, say they simply apply classification, classifying count, like in sentiment classification of tweets. So, social sciences. Okay, so we have already seen two examples. Okay, so classifying by happiness, classifying according to sentiment of mentions of politicians and the like. So in general, why do I mention the social sciences? Because the social sciences, the political sciences, are disciplines in which individual cases hardly matter, okay? So social scientists are inherently interested in aggregate results, okay? So the goal is actually obtaining quantitative indicators about a specific population, okay? So a population which can be broken down by age group, by gender, by state, by region, whatever, okay? So as these two social scientists put it, I mean, they say that others may be interested in finding the needle in the haystack, but social scientists are more commonly interested in characterizing the haystack, okay? Getting the aggregate statistics, okay? And there are scores of other applications, okay, ranging from predicting election results, emotional responses of the population, etc. This very idea of using social data, I mean, social network or data originated within social network for doing social science studies has sparked an entirely new field, which is called computational social science. And this is the big new wave, the big new paradigm within social science, which has witnessed a sort of an increasing abandonment of the typical means of doing social science, which is the survey, in favor of, let's say, gathering data emerged from social networks, okay? So, I mean, it's a shift from actually eliciting people's responses to actually harvesting people's feedback that has been generated independently. Okay. Epidemiology. I mean, we've seen one example of an application that has to do with quantification, that is screening tests. There are others. Okay. So epidemiology is very similar to social sciences. Okay. So there is only interest in the aggregate data and not on the individual data. And so one way of doing epidemiological research is taking clinical records, say radiology reports, and classifying them and taking aggregates. Okay, so by doing this, you actually can track the relative incidence of different pathologies. Okay, and I mean this is quite interesting because not only you can actually study trends, but you can detect problems before they become, say, epidemics. Okay, so this is quite important. One interesting application, which is a bit peculiar within epidemiology, is what people call verbal autopsies. Okay, so this is especially important in developing countries. Okay, so just imagine, say, remote African villages where people die, but there is no doctor there to actually certify that the cause of death was X or Y, actually. So, I mean, what do people do here in order to estimate causes of death? Well, I mean, they do a sort of classification, okay, because in order to generate a so-called verbal autopsy, what you need to do is to say, in this case, I mean, ask parents or relatives or friends, so ask a questionnaire, get a sort of a textual description of the symptoms that these people was experiencing, and then sort of classify these symptoms. Well, in order to classify, where do you get the training data? Okay. So you get it in hospitals where this kind of death certification was available. So you get descriptions of the symptoms, typically by caregivers, and you get also the causes of death, which is certified by the doctors. So, I mean, the cause of death certified by the doctor is your label in the training data, okay? And the description of the symptoms is actually your vector X. So in your remote African village, you only have vector X, but in the hospital, maybe in the main town nearby, you have both vector X and label Y, okay? So you have the training data. And this is very important because, I mean, tracking causes of death is yet again a problem which is extremely important, I mean, for caregivers. It's of crucial importance for international health policy making, for channeling research efforts, for channeling aid efforts, etc. And again, I mean, here is a case where we are interested in quantification and not classification. And it's quite interesting, the fact that one of the today most interesting quantification methods actually was proposed by people doing verbal autopsies, and we'll come to it in a while. So another quite interesting application is market research, okay, and especially survey coding. What is survey coding? Survey is when, I mean, someone has a questionnaire, okay, for maybe for electoral purposes, opinion polls, for market research, for customer relationship management. So, I mean, people run a questionnaire and asking people questions. And, well, most of these questions would include closed questions. Okay, so most of these questionnaires would have mostly closed questions. It means you have to tick a box, which one applies to your case. But some of the questions might actually elicit a textual response. Okay? So when you have, say, 10,000 people who have answered the same question in a textual way, what are you going to do? Okay, so typically, people within market research would classify these questions according to a number of interesting cases. Okay? And there are actually a couple of different cases here. So take the first question. Okay? How satisfied are you with our mobile phone services? So this is a question that might be asked from a telecommunications company. And here the scientist might be interested in figuring out whether the respondent belongs to class may defect to competition or not. Okay, so I mean, to figure out whether this guy is so unsatisfied that he runs the risk of, let's say, subscribing to a competing service. Okay, so here the goal is classification at the individual level, okay, because we are interested in that particular customer because we don't want that customer to run away to the competition. But take this other, so I mean, this example is from customer relationship management. But take another example from market research, okay? So what do you think of the recent ad for product X, okay? Or say, what do you think about the idea of putting onions in the cheeseburgers, okay? I mean, this is something that a market research agency might ask. And the class of interest here could be LovedTheCampaign or loves onions in the cheeseburgers. And the goal here is actually quantification, okay? Because, I mean, the market research company is not interested in the fact that I like onions in the cheeseburgers. It's interested in the fact that how many, okay? Does the majority of people like onions in the cheeseburgers, okay? So actually here it's important, I mean, to quantify correctly the different classes. There are actually many other applications. Okay, so resource allocation is one that has sparked a lot of interest in let's say, in data mining. Okay, so resource allocation is when you have a customer support center. Okay, and the customer support center receives phone calls. Okay, receives phone calls related to several issues. And what the company would like to do is to quantify the amount of calls that are related to specific issues. Okay, so let's say Hewlett-Packard, their support center, might receive several calls related to printers, other calls related to drivers, other calls related to motherboards of their computers. Okay? So what their people would like to do is to quantify these issues in order also to actually improve the customer support, I mean, to devote human resources, I mean, to specific areas that need more attention, and that need more attention because people, I mean, ask for more. Okay. So essentially, I mean, if you are able to track class prevalences in real time, you can sort of identify rising problems before they become, as Foreman said, epidemics. Okay. So one interesting, you might have said, when are we going to see some applications for NLP? Okay, so this is one classic application for NLP, word sense disambiguation. Okay, so we all know what word sense disambiguation is. So the task of determining, given a certain occurrence of a word, the W in text, which sense of W is meant. So essentially, word sense disambiguation is a classification task, because if we assume that the different senses are predetermined, okay, we only have to classify each occurrence into the different senses. And one important fact here is that words or word senses have different sense priors. Okay, so different senses of the same word have different class prevalences. Okay, so word bank, typically in everyday English, is much more frequent in its sense of financial institution than in its sense as a hydraulic engineering artifact. Okay, so actually WSD algorithms do exploit these priors. Okay, when they want to find out the correct sense in which a word occurrence is meant. And the problem is that when you train a word sense disambiguation algorithm on one domain, well, you might want to port it to a different domain. But what if the different domain has different sense priors? So you're going to get suboptimal word sense disambiguation accuracy. Okay? So what people have done is to try to, let's say, train a word sense disambiguation algorithm on one domain and port it by actually first trying to estimate the new class priors in the new domain and adjusting the trained model to these new class priors. And this is the work of Chan and Ng, which appears in ACL 2006, and plus a series of other papers which have followed. Okay? So this is indeed a case of, say, domain adaptation, because what you basically do is try to refit a model that you have learned on one domain D1 to a domain D2. Another application that I want to discuss here is actually not an application, but what I would call a meta application, because the application is an application of quantification to doing better classification. And as we know, I mean, classification is a technology that applies to several different other fields. As I said, if we can do accurate quantification, we may be able to improve classification accuracy, because in the presence of distribution drift, classification accuracy suffers. Okay? So this relates to the question that Shafiq asked. Okay? So this is especially true if the classifier outputs posterior probabilities, and if the classifier picks the correct class by doing an argmax over all the probabilities. So this is especially clear, say, for the naive Bayesian classifier. So let's look at the formula. Actually, so the confidence in the fact that document X belongs to class CJ is also a function of the class prior, of the prior probability of CJ. Okay? So, I mean, if we compute this formula for all of the available classes and then take the class which receives the highest confidence, it's quite clear that the result is maybe influenced by the class priors. Okay? So if the class priors change, then the class that receives the highest score here tends to change. Okay? So it's quite clear that it would be beneficial to re-estimate these class priors here, I mean, to re-estimate how these class priors are in the test domain if distribution drift has kicked in. So, I mean, in general, what we say is that the probabilities, I mean, the posterior probabilities that are generated here in the presence of distribution drift, they are not calibrated anymore. So in general, I mean, we say that probabilities are calibrated when the frequency of the class is actually the expected value of the posterior probability. Okay? So it's typically the case that in naive Bayesian classifiers, the posterior probabilities are calibrated on the training set. Okay? But if the test set witnesses some significant distribution drift, the probabilities are not calibrated anymore. And I mean, trying to do quantification allows to recalibrate your probabilities to the new reality that you're going to tackle. Okay, and so adjust the classifier to yield better classification accuracy. So I mean, it's optimal Bayesian decision theory actually tells you, I mean, that in order to recalibrate your probabilities, you simply need to apply this recalibration formula, which is very easy because it says that the new posterior probabilities, okay, P, Cj, Wx, should be computed as the old posterior probabilities, I mean, the ones that you estimate on the training data, times the ratio of the new class priors versus the old class prior. Okay, so it's very easy to do this recalibration once, of course, I mean, you have estimated the new class priors, okay, which is the task indeed of quantification. This has been done in several instances, including semi-supervised learning. I will not go through, I mean, there are a bunch of other applications, I mean, some of them pretty esoteric, okay, including estimating different types of pets activity in wearable devices, okay, but I mean, this is not, this doesn't add much to our discussion, okay. So, I mean, now we will enter a more technical part, so, I mean, I would like to know if there are questions. Might be a good point to ask questions now. Okay. Okay. So, I mean, we've actually seen a sort of a motivational part for quantification now. And now I want to enter the slightly more technical part, which has to do, first of all, how we should evaluate quantification algorithms, and then in a part which actually will look at how to perform quantification in a way which is better than classifying count. So, evaluation measures, okay. So, I mean, there are 3 evaluation measures that I want to look at. And the very first one is probably the most obvious one, which is absolute error, okay. So, evaluation measure, of course, I mean, means trying to evaluate the quality of a prediction in the face of a gold label, okay. And when you have a set of classes here, essentially here I will take a single label multi-class classification as our default, okay. So when we have to pick one class, exactly one class out of k different classes, okay. So here, in order to evaluate the quality of our prediction, we simply take the absolute value of the difference between the predicted percentage and the true percentage in the gold standard, and we sort of average it out across all the classes, okay. So this is pretty straightforward. And what are the pros and cons? I mean, so essentially the pros of this measure is that it comes down to a very intuitive measure, which is very understandable also to non-initiates, okay. But one downside of this measure is that it doesn't really cater for the fact that when the gold, I mean, when the true percentage is small, then the error is more serious, okay? So I'll ask you to look at this case, okay? So suppose that the true percentage that we should estimate is 0.02, and our estimator estimates 0.01, okay? So that's the same absolute error as estimating 0.49 when we should have estimated 0.50, okay? But are these two mistakes equivalent? Not really, okay, because the second one is a fairly mild mistake, so 0.49 instead of 0.50, while the first one is pretty harsh, okay, because you estimate 2% instead of 1%. That's double the real percentage, okay? So, I mean, there's absolute error doesn't cater for the fact that different true percentages should be evaluated differently. And because of this, people tend to look at relative absolute error. In relative absolute error, it's essentially the same, but we have the gold probability, I mean, the true probability of the class at the denominator, okay? So, I mean that estimating, say, 0.1, while when we should have estimated 0.2 is much more serious than estimating 0.49 when we should have estimated 0.50. Okay. So the pros are, of course, I mean, that we relativized with respect to the true class prevalence. Here it's, and also the fact that it's anyway pretty intuitive. Okay. The cons is that this is actually, this measure is undefined when the gold probability of at least one class is 0, okay, because we have 0 at the denominator. And because of this, we need to introduce some smoothing, actually. So, which means that we typically add a small quantity epsilon to both the numerator and the denominator. And it's typically the case that this value is often used because it's actually half count, okay, so half of the value of an individual error. Actually, so relative absolute error is a reasonable measure, but the measure that has sort of stuck, that has become quite standard in quantification is Kullback-Leibler divergence. Okay. So KLD, which is also called normalized cross entropy, has this formula, and well, many of you would typically know KLD because it's sort of ubiquitous within language models, for instance. Okay, so it's a measure which is used quite often in order to estimate the dissimilarity, the divergence between a true distribution and a gold distribution. And this is what quantification is after all. Okay, so in a sense, using KLD sort of recognizes that quantification is all about measuring or estimating a distribution. Okay, so I mean this. The advantage of using KLD is essentially the fact that KLD has all good properties. I mean, it's all well studied within information theory, language modeling is well known, its mathematical properties are well known, etc. The cons of using it is that it's sort of hardly intuitive. Okay, so if you go to a customer, okay, and say, here's my quantification accuracy as measured, I mean, by my tool, and you present KLD values, and it's not really, it's a bit difficult to explain to non-initiates, okay? And also the fact that one problem is that it's got a sort of a clumsy range of values, okay? Because when we have perfect quantification, KLD is 0, while when we have very bad quantification accuracy, then the values goes to plus infinity, okay? So, I mean, the values are not entirely easy to manage, okay? And so, well, one idea could be, say, converting KLD value via sigmoid so that you convert them to 0, 1, etc. Anyway, I mean, so again, I mean, KLD suffers from the problem that it could be undefined when some true percentage is 0, and we need to do smoothing in order to solve it. So, as I said, I mean, it's become the sort of a standard for both single label and multi-label and binary quantification. It remains to be said that, I mean, this is not the only choice, okay, because KLD is sort of one of the many members of a family called the family of F divergences, okay. So lots of other measures have been proposed in the past to measure the discrepancy between distributions, and these could also be used in principle. This KLD gives a sort of a satisfactory answer to measuring single label multi-class quantification. But what about ordinal quantification? So ordinal quantification is, say, when we have, again, say, 5 different classes, 1 star, 2 stars, 4 stars, 5 stars, and we need to do quantification of them. Well, KLD doesn't take into account the distance between these classes. Okay, so it doesn't take into account the fact that, say, if I overestimate by, say, 5% the 5 stars classes, and that probability mass goes to the 1 stars classes, that's a more serious mistake than overestimating 5 stars and moving the same probability mass to 4 stars. Okay, so in a sense, I mean, we need a measure that accounts for the distance between these different classes. Okay? So the only measure which has been proposed up to now, which I proposed together with the past PhD student of mine, is what people call the Earth mover's distance. So it's something which in mathematics is also called the Wasserstein metric. And the Earth mover distance is, just to give you an example, so it's the distance that measures, or the kind of the minimum effort that that is needed to move probability masses from one class to the other by taking into account the distances. Okay? So it's called Earth mover's distance because it assumes that there is a worker that moves piles of Earth, okay, so that needs to move sort of Earth, okay, from one pile to the other, and its effort is measured not only by the mass of Earth that he needs to move, but also by the distance he needs to travel. Okay, so just to give you an example here, the idea is that here you have some overestimation of the very negative class. Okay, and in order to recover the true histogram, which is actually measured by the blue bars, you have to move this excess amount of probability, this excess Earth, to another class, to a class that actually misses that amount. And I mean, the more you need to travel down to this histogram, the more effort you do. Okay. So I mean, this is a reasonable measure, I mean, for ordinal quantification accuracy. It's reasonable, but it's certainly not optimal, okay? Because it's, if you look into it in detail, you find out that this is the ordinal analog of absolute error, okay? So it's, in the case in which if these classes, I mean, were not ordered, okay, Earth mover's distance would default to ordinal, to absolute error. So, I mean, it would be quite interesting to find out an ordinal analog of KLD, for instance. And this is, as far as I know, still an open problem. So if you want to, if you're an information theorist and you want to look into this problem, you will certainly give a contribution to the quantification literature. Another measure that I think has some interest is what people call multi-objective measures. Okay? So in machine learning, a multi-objective measure is a measure of accuracy that tries to simultaneously address different aspects of the result. And the use of a multi-objective measure in quantification has to do with what we have called the paradox of quantification. So let me recall that the paradox of quantification is the fact that we might want to prefer a quantifier that does more mistakes, but whose mistakes are more balanced across the false positives and the false negatives. So that, say, classifier A, I mean, which does 1,000 false positives and 1,000 false negatives, is paradoxically better in terms of KLD than classifier B, which only does 10 false positives and 0 false negatives. Okay? So, I mean, KLD for KLD B would be, in terms of KLD, B would be worse than A. But we sort of intuitively prefer A. Okay? And why do we sort of tend to prefer A? Because we think that, I mean, a classifier that comes up with this kind of results, okay, such as classifier A, is not really reliable. It's not really trustworthy. Okay? So there are a couple of papers in the literature. I mean, the first one is this, where I also participated, plus there is a paper by a group of Spanish researchers, which has just appeared, which sort of proposes to use as a measure, not just as a measure of accuracy, but also as a loss, okay, as something that you should internally optimize within a learning system, to use a multi-objective measure. Okay, so a measure that combines a measure of quantification error with a measure of classification error. So, I mean, the measure that, that the Millie et al. Paper uses is the following. Okay, so it's the absolute value of the difference between the square of the false positives and the square of the false negatives. Why is this so? Because, I mean, this is the product of these two factors. And the first factor, so the sum of the false positives and the false negatives, is actually a measure of classification error. Okay? While the absolute difference between false positives and false negatives is a measure of quantification error. Okay, so by attempting to minimize this measure, you are attempting to minimize quantification error and classification error at the same time. Okay, so it's quite likely the case that according to MOM, so classifier B is indeed better than classifier A, while classifier A is better in terms of pure KLD. Okay, so I mean, a multi-objective measure encodes the fact that, in our case, I mean, that we really want, I mean, we want good quantifiers, but we only want to restrict our search to quantifiers that are reasonable classifiers as well. Okay, and there is also, as I said, I mean, another paper which has recently appeared, which uses a different multi-objective measure, but I mean, the very idea is pretty much the same. In terms of how to perform evaluation, it's quite, I mean, the literature has sort of split between two different ways of doing it. Okay, so to what I here call two different evaluation protocols. Okay, so first of all, I should say that if you want to evaluate quantification, you don't need data sets which are explicitly devised for quantification. Okay, so, okay, you can use any classification data set. Simply, I mean, what you do, I mean, you would evaluate your ability, the ability of your system at estimating class prevalences instead of actually looking at the individual decisions. Okay, so the literature is sort of split according to what I call the artificial prevalence approach and the natural prevalence approach. So a lot of people have used this protocol in which they take a standard sort of a standard data set from the literature, which often comes with a standard split between training and test, and they conduct repeated experiments in which they sort of artificially vary the prevalence of the class or the prevalence of the classes in the training set and or in the test set. And they do this via subsampling. Okay, so the idea is that, say, if your class of interest in the training set accounts for 30% of your data set, so it's if the class prevalence is 0.30, you can repeat experiments by removing some of the positive examples so that your class prevalence becomes 0.25 or 0.20 or 0.10 or 0.01. Okay, so you artificially vary the prevalence in the test set by simply removing examples. And you can do the same in the test set, okay, so removing examples, I mean, from the positive class in order to test for several different types of distribution drift. Okay, so you can account for distribution drift in which the class prevalence increases from training to test, or even dramatically increases, or cases in which the class prevalence dramatically decreases from training and test. So this is what I call the artificial prevalence approach. And the pros of this approach is that you can vary at will and you can test different situations at will. The cons is that, to me, I think that sometimes, I mean, non-realistic experimental settings may come up, okay? And so, I mean, since a lot of experimental results reported in the literature average across different settings, okay? So these non-realistic settings may influence the averages a lot, okay? So in the past, I have preferred to work according to what I would call the natural prevalence approach, in which you try to pick a standard data set, which has a standard data set that naturally represents a wide array of class prevalences, and that naturally represents a wide array of distribution drifts. Okay? And here, of course, I mean, the cons is that you cannot vary at will this kind of drifts, you cannot vary at will the class prevalences, but the pros are that the experimental settings that you're going to test are sort of tend to be realistic because they are actually embodied in a true data set which represents a sort of a real life application. So I guess that we should have a break at 3:30. Is this correct? Yes, okay. So I'll start for 10 minutes to go through, to start with the fourth part, which is the more meaty part, and which actually is going to tell you a bit about methods that have been proposed in the literature for performing quantification, and that all have to do with the supervised learning. Well, sampling, what people call sampling, is not really a method, okay, and doesn't have anything to do with supervised learning. Sampling is something which is sometimes used as a baseline, and the very idea is that you don't try to do quantification at all. You simply say, well, I mean, if in my training set, I mean, the prevalence of my class is 30%, I assume that it will be 30% also in the test set, okay? Well, why do I mention this method at all? I mean, why do I call this a method at all? Well, I call it a method because, I mean, some people have used it as sort of a naive baseline, and some people say, well, if a legitimate method cannot outperform this baseline, then it's no good, okay? Is this true? I mean, I have a personal opinion, and my personal opinion is that sampling is not a legitimate baseline, okay? Why is it not like this, okay? Because, I mean, if you try to solve quantification at all, you sort of assume that you cannot assume that the class prevalence is the same, okay? So suppose you have a customer, okay? So your customer comes up to you and say, hey, I mean, I want you to track the level of satisfaction in my product throughout the next 2 years. And this level of satisfaction, I need a report every month, okay? So, I mean, suppose that he brings you training data, okay, which say that the level of satisfaction for his product is 35%, okay? What if, I mean, if you, in the next 24 months, you bring reports that always say this is always 35%? It's not a solution. It's a non-solution, okay? So, I mean, in a sense, people, I mean, George Foreman, I mean, one of this guy who initiated or, I mean, gave big contributions to the quantification literature said that in quantification, you fundamentally need to assume shifts in the class priors, okay? So if the class distribution doesn't change, you don't need an automatic quantifier. So you don't need to generate a product. I mean, you shouldn't be paid by your customer, okay, to always report 35%, okay? So what I normally say in experimental studies, let's forget sampling, okay? Let's not even use sampling as a baseline because it's not a legitimate baseline. Of course, I mean, this is a baseline that in some cases might outperform your legitimate quantifier, okay? Because if you take a data set, I mean, that has no distribution shift at all, of course, I mean, it's going to be the optimal baseline, okay? Of course, it's going to outperform your system, okay? But this doesn't mean that it's a better solution than your system. Paco?
I was thinking, it's not your lower bound. I mean, if you have a good learning algorithm, you should at least ensure that you're learning distribution in the training data.
I mean, sometimes some people have claimed that that's a lower bound. Okay, so people have claimed that that's a baseline. Okay, something that your method should outperform. My claim is that if any legitimate method doesn't outperform that, my claim is that we are looking at the wrong data set, okay? Because, I mean, a data set where class priors don't change, okay? First of all, it's probably a fairly artificial data set, but then it's not a good data set for studying quantification methods, okay? So to me, I mean, it's, you should go for, I mean, when there is an interest, say, in monitoring class prevalences across time, okay, you should prefer a system which is not optimal in the case when the environment is stationary and does some mistakes, but a system which performs reasonably well when your environment changes, okay? In which case, I mean, sampling generates disastrous results, okay? So, in a sense, I mean, a legitimately engineered quantifier is less risky than simply using sampling, okay? Because sampling, I mean, can give you disastrous results, okay? Although it may give you optimal results in some very specific cases. Alessandro?
It depends on the size of your sample. So if you have for the large number rho, of course, if you have a large sample, you are going to have a high accuracy in estimating the probability on the best vector with the same distribution. But if you have a small sample, in a perfect classifier, you are going to be much better in your test set than in the sample. Because there are some variation for the large number rho. And
I'm not entirely sure that...
You go to inspect exactly the distribution of the set that has some variation that is also quantifiable.
I'm not entirely sure that the size of the sample has anything to do, you know, with quantification. Because if you take the terrorism example that I made, I mean, from backlogs of 2001, I mean, irrespectively of the size of the sample, there, I mean, a legitimate quantifier would return reasonable results. I mean, sampling would disastrous, you know. It's irrespectively of whether you have chosen a small sample or a...
I was just commenting your case in which you have the same distribution. Even if you have the same distribution, using your automatic classifier,
all right,
this set can still give you something better than your estimation of the trace set.
Yeah.
But just
okay.
Not super important.
Okay, let's forget about sampling and let's look at real methods. Okay, and when it comes to real methods, we need to distinguish between two classes, okay, which people have called aggregative quantifiers and non-aggregative quantifiers. So aggregative quantifiers are sort of the standard methods, okay? So these are methods that actually require that each individual item is classified before, I mean, a class percentage is estimated, okay? Non-aggregative quantifiers actually are instead algorithms that don't even require individual classifications as an intermediate step. Okay, so they simply take the entire mass of the items on which quantification should be performed, and they take a decision that they estimate a percentage without having each individual item classified. Okay, so we'll mostly look at aggregative methods because most of the methods that have been proposed today are aggregative, but there are a couple of ones that are non-aggregative in nature. And among the aggregative methods, we may make a sort of further subdivision. Okay, so one is the methods that use general purpose learners. Okay, so a general purpose learners could be something like, say, SVMs. Okay, so typical SVMs, I mean, are used for several applications. Okay, so here we use the SVMs with a linear kernel to classify each individual item, and then we do some post correction in order to come up with better class estimates. Okay, so I mean, all of the methods that we are seeing in the general purpose area can use any supervised learner at your choice. Okay, so they could use SVMs, they could use KNN, etc. Instead, I mean, the second class is the method. I mean, a class of methods which use special purpose learners. Okay, so the idea here is to come up with learning algorithms that are especially oriented to doing quantification and which are not necessarily good at doing classification themselves. I think that this might be a good time to stop, correct? And we'll resume in 15 minutes? 30 minutes? 30 minutes. Okay, so this is 3:30. We'll meet here at 4. And I'll be here to take questions, I mean, in case some of you wants to come up and ask.
This distribution estimation is a fundamentally different problem for two reasons. One, you give the example of the wall, black and white walls with the error. And so sometimes you don't know how to classify which one is one or the other, but that's really a classification problem. This is not really a quantification, so much a classification problem, because even if you didn't know how to classify them,
what I think is that in density estimation typically assumes that you don't have a subjectivity.
Sure. So it's open to somewhere class the problem where you do know where the problem is objective, not subjective.
Right.
That issue you mentioned was you couldn't count.
Yeah, because it's in density estimation you sort of assume that your population is too big to allow actually examining each item in the population and getting a label for each item. Yes, yes.
Like you said here, you can just count, but then you can just count the whole sort. So isn't it really essential? I still don't see the distinction between the two problems. Just about the
Let's say in
Counts. In the second method, you estimate via summing posterior probabilities. Yes. Okay, let me. I think I'm running a bit long. Okay, so we should finish at 5:30. I guess.
Yes.
Okay. I'll
Take your time.
okay. I'll try to be a bit quicker on this. Okay, so. Actually, there had been George Foreman who did the bulk of the work on quantification in the mid-2000s. He observed that ACC, which is up to now one of our best methods, is very sensitive to the decision threshold of the classifier. Okay. Why is this so? Okay.
Sorry.
Yes.
Isn't that the case with all the metrics? I mean, isn't quantification itself sensitive to the classifier?
Oh, it's sensitive to the decision threshold of the classifier when you have decision thresholds. Okay, so TACC and TCC are not sensitive to this because you don't use the thresholds. You use the original raw posterior probabilities.
But I mean, still, you know, any even if you use the probabilities. Depends on the classifier itself.
It depends on the classifier,
you can
not
have
on the thresholds.
You can have a panel of classifiers, different classifiers, and each one is going to give you different results in the quantification.
Yes.
Right.
Well, I mean, sure. I mean, you certainly. I mean, every method is dependent on your classifier. Okay. But Foreman's point here is that these methods, aside being dependent on classifiers, they are heavily dependent on where you place the threshold. I mean, the threshold that separates 1 from 0. Okay, because normally a classifier returns you a score, a numeric score, and you have to set a threshold where, I mean, above the score you take it to be 1, below the score you take it to be 0. So I mean, probabilistic classifying count doesn't depend on any threshold because you sum over raw posterior probabilities. And here, actually, he observed, I mean, that this dependence on the threshold
can yield very unstable results, especially when we are talking about infrequent classes. Okay? So take a binary classification class in which the positive class is very infrequent. Okay? So in this case, essentially a classifier like you know, SVMs with linear kernels, you know, and which are tuned for standard accuracy, will typically generate classifiers which are very not lenient, but sort of conservative classifiers that tend to be tend to say no, okay, because this ensures very high accuracy. Okay, so if you tend to say no, your true positive rate will be very low. Okay, and also your false positive rate will be very low. So you will almost never return a positive answer, be it correct or incorrect. Okay? So this denominator might well be 0 or close to 0. Okay? So when it's 0, I mean, this is a disaster because this is undefined. Okay? When it's close to 0, it means that it's very unstable. Okay? Because the probability will be very high and very subject to fluctuations. Okay? So I mean, he essentially, I mean, this is a correct observation. I mean, what I don't agree very much with is what he did, you know, in order to solve this problem. Because what he proposes to do is to pick to actually perform a just classifying count by a threshold which is different from the natural one that you would pick. Okay? So he would propose to pick thresholds that, let's say, make it so that this number is not 0 or is not close to 0. Okay? So there are scores of, there are several methods that he proposed here with different heuristics. Okay? The problem is that, I mean, if you look at the methods, I mean, that they don't sound very, I mean, they sound very heuristic, and they are such that, I mean, quantification gets even more unrelated to classification than it is normal. Okay? So one of the method X, he suggests to set the decision threshold in such a way that the false positive plus the true positive rate is 1. Okay? Or maybe this method in which he says, I mean, we try to maximize this difference here so that we maximize the denominator. Okay, fine. Okay, so this makes the class prevalence, you know, more stable, but there is hardly any theoretical rationale behind it. Okay, so I mean these are several heuristics and several methods which have been proposed in the literature, and indeed, I mean, our experiments show that they don't seem to be very good ideas either. Okay, so ACC, the original ACC, adjusted classifying count, tends to outperform all of them. Okay. I want to discuss some more theoretically grounded methods, and one is this very interesting mixture model. So the mixture model essentially consists of assuming that, of looking at the distribution of the scores that the classifier assigns to the test examples. Okay? And the idea is that this distribution should be, I mean, the hypothesis is that the distribution is a mixture of two other distributions. So the distribution that, the score distribution that the classifier assigns to the positive examples, and the distribution that the classifier assigns to the negative examples. Okay? So you may, it's a reasonable assumption that these two distributions are different, and of course, I mean, that the total distribution that you can observe is a mixture of these two unobserved distributions with these two parameters, okay, which is the probability, I mean, the frequency of the positives, and here is the frequency of the negatives. So you can observe that indeed, I mean, if we could reliably estimate this distribution, and if we could reliably estimate this distribution, then, I mean, and we can observe this in the data. And so the remaining parameter is what we really want to estimate. Okay, so the class prevalence. Okay. So this method is actually consists of estimating the two distribution, the distribution of the scores in the positives and the negatives via k-fold cross-validation, and picking as the value of the class the ones that returns the best fit between the observed distribution, the distribution we observe in the data, and this mixture. Okay, so estimate this, observe this, and so okay, this is the result, and this comes out as a result. And there are, different variants of this model that have been attempted. Okay, so which differ actually in terms of how the goodness of fit between the left and the right side of the equation is are tested. Essentially, these are two methods to estimate the goodness of fit or how the two distributions actually fit with each other. We have again subjected these to tests, but yeah, unfortunately, the original ACC method still comes out on top. So it's yet sort of not a very good method in practice. So this is a much more, this is a very, very interesting method instead. So this belongs to the class of the alternative methods. And this is why I think that the methods we have seen up to now are the ones that come from the data mining literature or the statistics literature. This is what I would say the method which was most influential between the methods that were proposed from machine learning literature. So this is the method that was proposed by Marcus Evans and colleagues back in 2002, and it's a method based on the EM algorithm. Okay, so expectation maximization. So the very idea of this method is start from starting from the idea of computing the likelihood of your test set. Okay? And the likelihood of your test set, and you can essentially be described as the product of the probability of each document in the test set, which, for the law of total probability, is the product of the sums of the probability of each test document given the class times the probability of the class. Okay? So again, you see that there is this probability of the class that is something that we want to estimate. So these are the so-called within class densities, which are assumed constant in the training set and test set. And so the idea of this method is to determine the estimates of the class probabilities that maximize the likelihood of the test set. Okay? And when it comes to maximizing the likelihood, EM is the sort of the default method that comes to mind. So EM, for those of you who don't know, is expectation maximization. It's an important algorithm, iterative algorithm for finding maximum likelihood estimates of parameters for models that depend on unobserved variables. Okay? And this case, in our case, the parameters are the class priors, okay? So the PCs we want to estimate, and the unobserved variables are the class labels, okay? Because we don't know the class labels from the test set. So this EM method is an interesting iterative method in which we run a method. We run an iteration which alternates between the two steps, the so-called expectation step and the so-called maximization step. So let's look at the iteration. Okay? So the initialization, step 0, so in each step we compute a posterior probability, so the posterior probability of the class given the example, and we compute a new class prior of the class. Okay? So we initialize the algorithm by saying, well, our initial class priors are the ones that we estimate from the training set. Okay, easy. So normalization, we iterate these two steps. Okay? So we first recompute the posterior probabilities in the way that we have seen earlier. Okay? So the posterior, we essentially recalibrate the posterior probabilities given the new priors. Okay? So we take the old posterior probabilities and we multiply by the ratio of the newly computed priors divided by the maximum likelihood priors. Okay? And this is just a normalization factor. So we have recomputed the posteriors. Once we have recomputed the posteriors, we can use them to recompute the new priors. So this is the calibration step, say, simulation step, in which we recompute an adjusted prior for class Cj by simply summing over the newly computed posteriors over the entire training set and taking the average. Okay? So essentially, this iteration alternates between a new computation of the prior, a new computation of the posteriors in terms of the new priors, and a new computation of the priors in terms of the new posteriors. Okay? So I mean, you run this algorithm until some sort of convergence. And the convergence means that you have recomputed your priors, which is what we are interested in, and you have computed the new posteriors. So essentially, this is yes.
This is essentially what the semi-supervised using EM does. So I think this is the same.
Yes. So this is a very sort of straightforward application of EM to the case of computing, to estimating the class priors. And yeah, the interesting fact is here that as in all machine learning literature on quantification, essentially the class priors are not interesting per se, but they are used in order to recalibrate a classifier. Okay? So to improve the accuracy of your classifier, so to tune your classifier to the changed conditions of your test set. Okay? So you train your classifier with the training set, but then your conditions have changed. You need to apply them on test set, and so you try to figure out what the conditions of your test set are in order to recalibrate your classifier. I think this could be called something like transductive learning. Okay? It's probably falls within transductive learning. And I mean, this method is interesting, especially historically, because this is the first method that was proposed for quantification within the machine learning literature. And another observation is that if, say, we have an initial guess of the values of the new priors, of course we can use them in order to initialize, the priors. Okay, so in order to have an algorithm that converges better, converges much more speedy. Second observation is that the method heavily depends on the initial posteriors. Okay, so the initial posteriors had better be calibrated in the beginning if you really want to convergence and to speed up even. Okay, there are some variants here that have been, but I think I will skip. Okay. I want to deal instead with a topic which I think is more interesting, maybe because we were the proposers of this approach. So essentially, the methods that we have seen until now are aggregative methods, because they classify all the instances in the beginning, and they are based on general purpose learners. Okay, so we use the SVMs with linear kernels. So here I want to look at aggregative methods that are based on special purpose learning. And so I mean the idea is that if you come up with a special purpose learning algorithm which is optimized directly for quantification, I mean it's good because in a sense you're showing that you address quantification as a task in its own right. And in a sense, if you optimize for a task, there is a promise that you can deliver better accuracy. Okay? There is a bit of a con here in this approach, in the sense that optimal classification and optimal quantification diverge. Okay? So if you want they require two different learning processes. Okay? So one which is addressed to quantification, the other which is addressed to classification, and the two are not necessarily aligned. Okay? So what is the basic idea? I mean, this is a paper which is going to appear soon in Transactions AD, and the idea is very, very simple. Okay? So the idea is that we want to apply explicit loss minimization. So we would like to have an algorithm, a learning algorithm, which directly optimizes for the evaluation measure that we are going to use when evaluating the results. Okay? Well, that's a bit of a problem in our case, because in standard algorithms, most learners say SVMs, okay, say Adams or Galactic, I mean, are optimized for standard accuracy and 0-1 loss or variance, such as the hinge loss or whatever. The problem is that, I mean, if you optimize for base, if you use these on imbalanced cases, I mean, where positives are much in fewer numbers than the negatives, optimizing for this kind of losses is sort of suboptimal. Okay? So, because the classifiers will tend to make, will have a tendency to make negative predictions, okay? So, to the detriment of quantification accuracy. And we saw this in the result that I reported. Okay? So, I mean, all of these very big data sets, okay? More than 5,000 binary test sets, I mean, using optimized linear kernel SVMs brought about an FN ratio of 0.109, okay, while 1 would have been the optimal. Okay. So, I mean, the idea is that here we are trying to directly optimize, I mean, for the measure we are going to use in evaluation. The problem here is, suppose we are using KLT. Okay. Can we tune standard SVMs to optimize KLT? No, okay, because most learners, such as standard SVMs, but also others, etc., they can be optimized for measures that must be linear and univariate. Okay? So linear means that the error on the test set is a linear combination of the error uncovered by each test example. Okay? Is this the case in quantification? No, because I mean, if you paradoxically, I mean, if you have many false positives and few false negatives, okay, if you do another false negative, okay, another mistake, it will be beneficial. Paradoxically, it will be beneficial because it will rebalance, I mean, the number of false positives and false negatives. So essentially, any kind of measure that we might want to use for quantification is essentially non-linear. And any kind of measure that we might want to use is multivariate, in the sense that the measure must take into consideration all of the elements at once. Okay? So you cannot run the evaluation by evaluating on each individual test examples. Okay? So you need methods, learning methods that can be optimized for non-linear and multivariate accuracy measures. Okay? So I mean, what we did, we actually employed one learning method, which is the SVMs for multivariate performance measures, okay, so SVM perf. So an algorithm was proposed by Torsten Joachims something like 9 years ago, and we tailored this algorithm to directly optimize KLT. So this is a very easy, very basic idea. Okay. So SVM perf is essentially a specialization to the problem of binary classification of the class of algorithms which are called SVMs for structured prediction. Okay. So this is a class of algorithms that can, I don't know if you actually followed the tutorial by Martins a few days ago, and which was all about structured prediction. Okay. So structured prediction means that your learning algorithm can't just predict labels of individual unstructured items, but can label trees, graphs, or any kind of complex structures. And the kind of structure we are looking here is the set. Okay, so we have a set of items which we have to individually label. But the idea is that we have to label each individual item depending on the kind of labels that we attribute to the other items. Okay, so essentially, SVM curve learns classifiers that take an entire set of, instead of taking one, say, document and return a label, they take one set of documents and return a set of labeled documents. So the idea is that they take conceptually a batch of documents all at the same time. Okay? They attribute labels in a way which is interdependent. Okay? So actually instancing these to KD was very easy. And the interesting fact is that the results were very, very good. Okay? So it's predictable, okay? Because it's essentially what you do, you tell your learning system to go for that measurement that you're going to use. Okay? You see that this is the results for RCD1, okay, but the results for Ocean are similar. And the SVM KLD basically outperformed all of the other baselines that we have seen up to now, even by large amounts, especially in the very low prevalence and low prevalence classes, and performed pretty well in the high prevalence and very high prevalence classes. But overall, across all of the entire classes, it's significantly outperformed all the other baselines. Here we see, you can see the results, chopped up in 4 classes, which is a slightly different way of chopping up from the ones that we have seen before. Before we had seen chopped up according to drift. Okay, so one data set exhibits very high drift with respect to the training set. Here we chopped up according to prevalence. Okay, so here we are looking at classes which have very low prevalence with very frequent classes, and here this is instead the very frequent classes. Okay. So you can see that if you have a data set which is varied enough, you can do lots of different tests and lots of different ways of chopping up the results and studying the individual cases. Okay. So here actually you can see results in which instead of sheer accuracy we tested variance. Okay. So the fact that whether the results of the system are stable enough across the same bin. And again, you can see that the SVM KLD exhibits a very small variance, okay, which is good, okay, because it means that it's pretty stable. Pretty stable.
There is a drift of fixed drift anyway.
This is irrespective of drift. This chopping up is irrespective of drift. Yes, it's. You can take these 5,000 data sets and chop them up by drift or chop them up by prevalence. So these are.
Since you are telling here that you divide the set
by prevalence.
Where instead the main.
This is the prevalence in the training set.
Yeah, the main aspect.
Sorry, the prevalence test.
Yeah, but you always test on distribution that have some drift. So I imagine that you are using some fixed drift for feeds there.
No, because in the 5,000 different data sets, we witness all kinds of drift. Okay. So there are here in this bin there might be data sets which exceed high drift and other data sets which exceed low drift.
I think what he means is that how can you ensure there's no bias in particular those prevalences with respect to drift? So you're saying that drift is uniform across the whole 5,000 data sets, but can you?
No, it's I didn't say that. Okay, so it's this is 5,000 data sets that exhibit very high, some exhibiting very high drift and some exhibiting very low drift. Okay.
So did you fix the drift across all of them?
No. I mean, it's each. I simply say that I mean you have a large number of data sets, 5,000 data sets, right? So you can bin these data sets into different bins. Okay? But the way, I mean, one way to bin them would be according to prevalence in the test set. Okay, prevalence in the set. Okay, so here this is what the way they have been binned. Okay? So here we are looking at data sets, okay, where the classes are very infrequent. Okay? So I mean, the binning here is according to class frequency. Okay? But another way, I mean, to bin them, which is completely orthogonal, which is completely independent, is according to the drift that that data set, that piece of the test set, exhibits with respect to the original training set. So I mean, what I mean here is that in these results, I mean, you witness very different types of drift. Okay? So it's not a dimension which is used for binning. Yes?
Can you just give an idea of what you consider to be a very low prevalence and a very high?
Oh, very low prevalence, I believe here means smaller than 0.1%. Very low prevalence. I think that low prevalence means between 0.1% and 1%. High prevalence between 1 and 10, and very high prevalence means above than 10%. You know, because in text classification, so in text classification, the K, which is K is here, okay? So essentially imbalance is the norm rather than the exception. So one of the classes here has a prevalence of 0.53. This is very unlikely, you know, very, I mean, only in some peculiar text classification cases you find balanced data sets. So, I mean, even a prevalence which is, say, 5% is considered a high prevalence. But actually, I can direct you to the paper where all the details for the B. Yes?
So I'm not sure if this is just an intuition that I have, but for the low prevalence class, for the aggregate area, wouldn't it be more difficult to measure drift because the classes are so infrequent, so that you might not be able to?
So the question is if for the low prevalence or very low prevalence class, drift is more difficult to
I'm not sure, would it be more difficult
to compute?
To measure, yeah. Because of what we see is noise.
No, I mean, you have a formula for computing drift, which is K and D.
Yeah, yes, I know.
It's not difficult.
The measure I know, but what I mean is like how can we be sure that this isn't just noise in the data set that we have? So it's something.
Well, I mean, you count noise. Well, all data sets are noisy, you know, so essentially this RCD1, I mean, Reuters Corpus Volume 1 is very low in noise because this is professionally annotated stuff. Okay, so it's something that originates from Reuters, where it's professional editors who attach labels. Okay, so it's. But anyway, I mean, all of the experimentations that is run for quantification, I mean, doesn't take noise into account. I mean, takes the data sets at face value, you know. So it's probably an orthogonal problem. Yes. I think I should run a bit now. And let me check what are the most. Yeah, I think that I want to, at least in the 10 remaining minutes that I have, I want to at least discuss one method which is non-aggregative. Okay, so this is quite interesting. Okay, because this means a method that tries to come up with class
well, class prior estimates without even attempting to classify individual items. Okay, so this is a method that was proposed by these guys. I mean, King and Liu. I mean, these are essentially epidemiologists. Okay, and you might remember that I talked about verbal autopsies. Okay, so autopsies for causes of death. I mean, from third world countries where causes of death certification is not available. Well, that was a study, I mean, where this method was proposed. Okay, and it was later popularized in another publication, Hopkins and King, which essentially talks about blogging about political candidates. Okay, so it's quite funny, I mean, that the second publication is much more better known than the first one. Anyway, the idea is to estimate class prevalence directly, I mean, via application of this formula. Okay, so let's try and read this formula. Okay, so this is again an application of the law of total probability, which says that the probability of the vector x in the training set is the sum across all of the classes, okay, of the probability of x given Cj times the probability in the test set of Cj. Okay, so I mean the form of this equation shouldn't surprise you. Okay, so again, low total probability. Let's try to figure out what it means in practice. Okay, so first of all, I mean, we have here the probability in the test set of Cj, which is what we want to estimate. So it makes quite clear that if we have these two factors, again, I mean, if we can estimate this and we can estimate this, we obtain this as a result. Okay, so the problem is essentially the fact that the estimating the probability of vector x in the test set cannot be done reliably, okay, because x is high dimensional, okay. So this is a problem that we know very well, I mean, from Bayesian probabilistic classifiers, and this is a problem that indeed justifies, I mean, the naive bias assumption according to which the probability of the vector is the product of the probabilities of the individual features in the vector. Okay, so essentially, I mean, this is essentially the idea that these people exploit. So what they do is say, they propose using subsets of this vectorial representation in place of the original representation, so that, in a sense, I mean, the probability of a given subset, I guess that K here indicates length, okay, of a given the probability of a given subset of X is the sum across the classes of the probability of the subset given the class times the probability of the class. Okay, so essentially, I mean, what you can do is to estimate the probability of Cj several times by estimating, again via k-fold cross-validation, the probability of Sk and this probability and this conditional probability for different choices of this subset. Okay, so once you do it, okay, you can take all of these estimates of PCJ, which are competing, and I mean, you take, say, the median, since the median is a fairly robust estimator. Okay, and well, suppose that as subset, you take subsets of length 1. This is clearly reminiscent of the, you know, Bayesian independence assumption that we do in naive Bayes classifiers. Okay, so I mean, this is essentially one of the. This is a method that I sort of discovered fairly late. I mean, so this method and the EM method of Serens, I mean, we haven't run comparative experimentation with the other methods, but this is something that I want to test, you know, because I mean, it's very interesting from the theoretical point of view, because as you can realize, I mean, it does an estimation of the PCJs, I mean, without even attempting to individually classify each of the individual items, you know. So it's quite interesting from a theoretical point of view.
On
X is the entire feature vector. Okay, so
The whole instances, like all the instances. Or
you can, well, yeah, I mean, it's one instance, okay, but you can do it for several instances. I mean, so you can, your median is going to be a very robust, you know. So, I mean, you can, essentially you have two different dimensions, okay, so it's, you have several instances, and for each instance you have several possible subsets, you know, which is, you know, brings about a lot of estimations of PCJ, I mean, so that your median is going to be extremely robust. That's the argument.
But essentially this is a Bayesian predictive, what it does, it's the same thing. Like you take the weighted average of the class prior with the class, with the condition, and you estimate the posterior predictive distribution. It's the same that the Bayesian view of.
Yes, I think so, yes. Okay, let me discuss, I mean, in terms of which method performs best, you know, as usual, I mean, it's not, there's no conclusive evidence in the literature, okay? One of the reasons is that, as you might imagine, I mean, different papers use different data sets, different papers use different baselines, different papers use different experimentation protocols. I mean, something relying on, you know, naturally occurring prevalence or naturally occurring drifts, or something artificially devising this drift, okay? So, and I mean, this is a bit exacerbated by the fact that there is no shared task, okay, on quantification yet. So, I mean, we don't have much conclusive evidence on which works, okay? So this is a sort of a matrix in which I've tried, I mean, across, I mean, a number of algorithms that I've discussed today, I mean, to illustrate, I mean, which paper actually proposed which algorithm, which is indicated by the circle, and which paper used which other algorithm as a baseline, okay? So you might notice, I mean, that several papers, I mean, proposing a given algorithm only use one baseline or use very few baselines, okay? So it's, I mean, again, concluding experimental evidence on which algorithm performs best is not easy, okay? So the one that I've, the experimentation that I've discussed today is, well, I mean, the ones from our paper, okay, not just because it's us who did it, but because it's the experimentation which works on the largest data sets and the ones that tries to compare with the biggest amount of baselines possible, okay? So, but still, I mean, evidence has to be accumulated yet. Let me give you a couple of words about efficiency, okay? So computational cost, okay? Which methods are the most efficient? So, I mean, today, as I said, I mean, the only large-scale comparison is the one we run, okay? We compared 11 different methods. And it turned out, I mean, that certainly the cheapest one is classify and count, okay? And the second one is SVM KLD, okay? So the ones that we proposed, okay? Why is this so, okay? Well, I mean, SVM KLD is more expensive than CC because essentially, I mean, it's quite evident, I mean, that linear SVMs are, let's say, computationally less expensive than SVMs for structure prediction, okay? But essentially, I mean, SVM KLD turns out to be second fastest because, I mean, SVM KLD, like SVM perf, I mean, the one proposed by Thorsten Joachims, essentially is parameter free, okay? So it's, there is no need to do costly parameter estimation from k-fold cross-validation. While k-fold cross-validation is essential in all of these other methods, okay? So, for instance, I mean, PCC, I mean, the probabilistic methods need to estimate sigma, which is a parameter needed in probability calibration. ACC and other methods need to estimate the probabilities of misclassification. So the mixture model instead needs to estimate the original distribution scores from the positives and the negatives, okay? So, and essentially, I mean, of course, I mean, the cost essentially depends very much on as a function of k, okay? So the number of folds that you use in k-fold cross-validation. So say George Foreman proposed that 50-fold cross-validation to be used in order to get reliable results from these methods, but this makes it very, very expensive to compute, okay? So for instance, I mean, in our paper, we found out SVM KLD to be something like 22 times faster than PACC or the like, okay? So EM sounds like a very efficient algorithm, but we haven't tested it in practice. I think that my time has run over. I will let you go through these slides, I mean, for advanced topics to look at. Let me just give you a couple of words in conclusion. So I think, I mean, I just hope that I have sort of stimulated your interest in quantification by this tutorial. I hope that maybe in this tutorial you have found out examples of tasks where you have worked at and in which you have said, hey, I mean, there is a quantification component here. Up to now I have used, I mean, I worked on it in a sort of a naive way by doing classify and count. I might try to improve my task by using a legitimate quantification method in order to improve my task, okay? So to use quantification as sort of ancillary in order to improve some other task. Even better, I mean, if you're stimulated into working on quantification as a task in its own right, I think that there are, I mean, this is a task which, despite the fact that early methods were proposed as back as 1966, it's a relatively unexplored task, okay? And so there are lots of sort of low-hanging fruits to pick, okay? So, I mean, methods, say, I mean, extending algorithms such as SVM KLD to the single label class, single label multi-class case. Still, I mean, for the moment being, that algorithm is still binary in nature, okay? So we don't know how to extend it to multi-class. Essentially, I think that quantification is going to grow in importance. Why is it so? Well, one reason is this big data bubble, okay? So big data is the very emergence of big data and data from sensors, from all kind of, from social network, from you name it, means that because of the sheer size of the data sets, we will more and more be able to only afford looking at the data from an aggregate perspective, and less we will be able to afford looking at the individual data. Okay, so big data essentially means looking at indicators that we can get out of them without really looking at the individual. So we will more and more be interested, or we will more and more be able to only afford characterizing the haystack instead of actually looking for the needle in the haystack. Okay, I think that my presentation ends here. And so is there questions? I thank you very much for the many questions you have asked, but if there are any other, I don't want to close the floor. So if there are no further questions, thank you. I mean, you can, if you have second thoughts about what you've heard today, I mean, you can email me, I mean, stop me in the corridors here for the next half an hour, or just email me with your further question. Paco, one.
Has anybody tried to use some sort of bagging methods, or try with different classifiers?
This is something I skipped, but I mean, there is a group of people in Pisa with which we actually published a paper in ICDM last year, in which we used quantification forests, which is sort of trying to exploit wisdom of the crowds effect And forests here means essentially a random set of trees, and we defined a thing called quantification trees, where essentially KLD or some quantification-specific measure is used as a splitting criterion.
Does it work better or not?
Yeah, the problem is that, decision trees and their equivalents, are not very good for text, because, the sheer amount of features that you have in text, makes the decision trees blow up.
But I wondered if you can do the same with some other not forest, but bagging with any other type of classifier where you train on a subsample of the data, or you use different set of parameters.
That's one of the low-hanging fruits. I don't think everyone has done bagging on this. Although, probably the method that I discussed here, the King and Liu method, where you do many different attempts, from estimating many different subsets here and taking the median, goes into the direction of, has a sort of a flavor of a committee, where the combination rule is the median, But yeah, sure, bagging, no, it has never been used, and this would certainly be something interesting to try. Okay, so thank you very much for your patience. So I think we might want to resume our tutorial, and so in order to give some time for the latecomers to come in, I will simply repeat the point where we have come at. Okay, so we have started looking at methods for doing quantification, and we have said that there are two main classes of such methods. One is the aggregative, and the second is the non-aggregative methods. So the aggregative methods, you should think of a method that, first of all, as an intermediate step, the method would classify each individual item. And as a second step, it should take the class estimates that this method returns and adjust them in some way. The non-aggregative methods, instead, they don't have such an intermediate step. So conceptually, they don't even classify the individual items. Okay, so they would come up with a class estimate, but they wouldn't be able to say, to provide examples. Okay, so they might come up with a prediction that says 28% of the elements are in the class, but they wouldn't be able to actually indicate some examples of these 28%. So the aggregative, in turn, they are, you can figure out two main classes. One is based on general purpose learners. So you could have SVMs with linear kernel, or you could have KNN decision trees, whatever. And so it means it's methods that can take as input any supervised learner and use that. Okay. Instead, the second class is special purpose learners. Okay. So it's learning algorithms that have been designed with quantification in mind. So, let's look at, well, we have, speaking of sampling as a sort of a naive baseline, okay, and said that we have argued that probably we shouldn't even consider that as a baseline. Classifying count is essentially what the typical baseline that we should use. And classifying count actually consists, as the name says, in training a classifier from the training set, from classifying the documents in the test set, and counting the number of documents that have been attributed the class, and taking that as the estimate. Okay, so just to familiarize with the notation, So this means that the estimation, which is indicated by hat, of the probability of the class in the test set according to the classify and count method is equal to the probability that J has obtained a positive decision. So we have decided positively for class J in the test set. So I hope the notation is crisp enough. So we have argued that one of the problems of classifying count is that a good classifier is not necessarily a good quantifier, because you might have a good classifier which is biased. So what is a biased classifier? So a biased classifier is a classifier that makes a number of false positives that is significantly different from the number of false negatives. And this is the fact that classifiers that we normally train in everyday life are biased is a fact of life, okay? And it's a fact of life especially when classes are severely imbalanced, okay? So let me make an example. So in text classification, we are often confronted with the imbalance problem, okay? So suppose that we want to classify web pages according to whether they are about nuclear waste disposal or not, okay? So if we sample the web, only 1% or less than 1% of web pages are about nuclear waste disposal, okay? So you have a 1% of positives and a 99% of negatives, okay? So it means that if for a classifier, it's much, so a trivial classifier that always says no would obtain a very high accuracy, okay? So would get it right 99%, okay? So it means, I mean, that if you train a classifier, I mean, if you lost the class, you train the classifier for, you optimize the classifier for, is simply the number of mistakes you do, okay? So if that's the loss you actually are trying to minimize, then you probably come up with a classifier that behaves very much like the trivial rejector, so the classifier that always says no, okay? So it means, I mean, that if you always say no, you would typically make a high number of false negatives, because you always tend to say no, and you will make very few false positives, okay? So you're going to have a biased classifier. So in a sense, I mean, standard classifiers like, say, linear SVMs are tuned to minimize either the total amount of mistakes or some proxy of it, such as the hinge loss or something like that, but not a measure that we instead are interested in, which is the absolute value of the difference between the false positives and the false negatives. So let me give you some experimental evidence for it. So we have run some recent experiments, okay, in which large experiments. So we had more than 5,000 binary classification test sets, each averaging more than 15,000 items. Okay, so that's a very large experimentation. So a standard linear SVM, okay, with all parameters optimized and bells and whistles, brought about an average ratio between false positives and false negatives of 0.109. Okay, so it means that these SVMs made 10 times or 9 times as much false negatives as false positives, okay? While the optimal ratio, okay, for classification, for quantification would be 1, okay? So this means that if you use standard learning algorithms, you are typically going to come up with biased classifiers, okay? So classify and count might give you good accuracy, good classification accuracy. They might not give you good quantification accuracy. Some people have, yes, Karim.
I mean, with linear SVMs, if you use it, let's say, for document classification, you typically want to do some sort of threshold adjustment so you can maximize your
Well, I mean, say optimizing your results for precision and recall is not very easy, okay? Because say, take F1, for instance, okay? So F1 is the typical measure we want to optimize for in text classification, but that's a nonlinear multivariate measure, okay? So, I mean, standard SVMs cannot optimize F1, okay? So you need to move up to, let's say, more complex learning algorithms that can optimize this, that can have multivariate nonlinear measures as losses that you can optimize. And we will see an example of this, okay? So I will probably come to this problem again, okay? But it's a fact that if we just use, let's say, a standard, okay, so learning algorithm, okay, such as, I mean, linear kernel SVMs, if you tackle a class which is imbalanced or heavily imbalanced, you are going to end up with a biased classifier. Okay. So, I mean, some people have argued that, a better idea than doing a classifying count could be probabilistic classifying count. So the idea is probabilistic classifying count is to leverage the posterior probabilities that a classifier might produce. Okay, so suppose that you have a naive Bayes classifier. Okay, so the naive Bayes classifier would return, for given a class, okay, would return a confidence estimate, okay, which is actually a probability. So the probability that document X falls in class CJ. Okay. So what a typical naive Bayes classifier, you would argmax over all of the classes, take and choose the class which returns the highest estimate. Okay. But I mean, some people have said, why don't we, instead of basically taking the final binary decisions, okay, why don't we use the original probabilities? Okay, because when you have an original probability and then you apply some sort of threshold on that probability in order to take a binary decision, you are throwing away important information. Okay, so the idea here is that the idea of the probabilistic classifying count is that your computed your estimated prevalence of class CJ will simply be the expected value of this probability. Okay, so you essentially take, you sum for all of the documents in the test set the probability, the estimated probability that X falls into CJ. You take the average of this, and that's your computed probability. So the benefit of this is that you don't throw away all of that information that you would otherwise throw away by applying a threshold. Okay, so it's actually you're going to use richer information, and so this is called the PCC method, and the people who have proposed it, I mean, unsurprisingly found out that it outperforms the CC. Okay. Actually, I mean, lots of classifiers don't return probabilities. Okay, don't return posterior probabilities. I mean, they return scores that are either not probabilities or are not necessarily within the 0-1 range. Okay, so in this case, what you can do is you can convert these scores into probabilities, typically applying a sort of a logistic function. The logistic function, for those of you who don't know, is a function which has this kind of shape and which converts, I mean, the entire range of real numbers into 0 and 1, and which is, I mean, a monotonically increasing function, which is the fundamental part. And here you see an entire family of functions, and the difference between all of these functions is this sigma parameter, which is a parameter in the generalized logistic function. And actually, which value of this parameter should you choose? I mean, in order to choose the best value parameter, I mean, choosing the best value of this parameter is what people call probability calibration. Okay, so the idea is that calibration consists in tuning this parameter in such a way that say if you have a training set of documents, the class prevalence in the training set is indeed equivalent, I mean, to the expected value of these probabilities. Okay, so I mean, it's essentially the average of the posterior probabilities over all the training set. So calibration means essentially finding good probabilities, and good probabilities is, I mean, the criteria for probabilities to be good is to actually comply with these constraints. And so, I mean, some people, especially George Foreman, whom, as we said, I mean, was one of the main proposers of quantification, the quantification task, actually dismissed the very idea, even without trying it. I mean, he dismissed the very idea of doing probabilistic classifying count on the grounds that, I mean, if the probabilities are, if the posterior probabilities have been calibrated on the test set, sorry, on the training set, they can be calibrated also on the test set only if there is no distribution drift. Okay, so I mean, he says essentially the very notion of wanting to do quantification rules out using the posterior probabilities. Okay, because I mean, we want, I mean, because we have distribution drift. Okay, we cannot, those posterior probabilities are not good anymore, I mean, once we apply them on the test set, okay? Of course, I mean, yes?
Is it fair to say that that's equivalent to saying that in that case we would have quantification accuracy be dependent on the classification accuracy?
Yes, yes, because it's, you know, I mean, when you have, let's say, I mean, the two go hand in hand, especially when your classifier outputs posterior probabilities. As we have seen, I mean, the very fact that you have distribution drift means that if your classifier outputs posterior probabilities, then those posterior probabilities are heavily influenced by the class priors, and your class priors have changed. Okay, so yes.
We have the same problem on the prior probabilities, because we use density estimation or quantification to get the prior distributions, and then use that for classification, and we also have density dependence.
Well, yes, I mean, but it's in a sense it's a case in which let's say probabilistic classifying count is a case in which we use say classification in order to solve quantification, and you say, I mean, that in order to do better classification, we should do quantification. So it's a bit cyclic, you know. So as I said, I mean, the machine learning people use quantification to improve classification, while PCC uses classification to do quantification, you know. So yeah, I mean, it's a bit cyclic as an idea. Anyway, I mean, as I said, I mean, there is sort of contrasting evidence in the literature that PCC might be a good method. Well, I mean, what we tried to do is to do some real experimentation on a very sort of large data set in order to figure out whether this is true or not. And indeed, I mean, in our experiments, we found PCC to be definitely worse than pure classify and count. And here I will start to give some experimental evidence in the form of these tables here. And so let me look at how these tables are organized. Okay. So for instance, here the experiments we run on two large data sets. One is called RCV1 V2, and this stands for Reuters Corpus Volume 1 version 2. So this is originally a text classification data set with made of Reuters news wires. And it's a very large one. It's 800,000 documents. And in order to do experimentation here, we have chopped up into several smaller data sets. And this data set is essentially 1 year worth of Reuters news. Okay. So, and the documents are organized into 99 different classes. And this is a multi-label document. Okay, so the same document can can belong to several classes. Okay, so essentially, I mean, this corresponds to having 99 independent binary classification problems. Okay, so essentially what we did, since this is 1 year's worth of data, we said, I mean, let's chop it up into weeks worth of data. Okay, so we have 52 different data sets, one for each week of the year, times 99 binary classes. Okay, so this comes down to more than 5,000 binary classification or binary quantification data sets, each with an average of 15,000 documents. So it's a pretty large experimentation, which, you know, tends to give reasonably reliable results. Okay, and here you can see that we indicate on the rows the different methods, CC and PCC, and you can see 5 different columns. What VLD starts for very large drift. Okay, so we actually took all of the 5,000 data sets and we did some binning. So we generate 4 different bins, according to which the data sets exhibited high drift with respect to the training set or low drift. Okay, so high drift is when the class percentage is very different from the one that used to be in the training set. Okay, and low drift means it is, I mean, the drift is very low. Okay, so the class percentage is very similar to the one that we had witnessed in the training set. So, I mean, we have 4 different bins: very large drift, very low drift, high drift, and very high drift. And all is a sort of the average across the two. So, I mean, if you, here you can see that on all of the 8 cases, okay, classifying count outperformed the probabilistic classifying count. So this, in a sense, tends to say that George Foreman's intuition was correct. Okay, so good question. I mean, what numbers are these? Okay, so these are the very clumsy number that KLD comes up, you know, with. Okay, so this and these values 2.43 for 10 to the -3, you know. So as I said, I mean, Kullback-Leibler divergence, I mean, generates values which are in between 0 and plus infinity. And the idea is that the smaller the number, the higher the quantification accuracy. So something which is E-3 is better than something which is E-2 or E-1. So it's an order of magnitude better, you know.
Is this SVM or classified?
Okay, so essentially means CC here was obtained via a linear kernel SVM. Okay, and PCC was obtained via a linear kernel SVM where the confidence scores were converted into probabilities via generalized logistic function. So I mentioned about this corpus. OSHUMED is a second corpus we worked on. OSHUMED stands for Ohio University Med. Okay, so this is a data set of abstracts from Medline. OSHUMED is a very famous collection in the text classification community. And again, I mean, it's substantially small. I mean, this data set is substantially smaller than RCD1, you know. And but again, I mean, the chopping up between different different bins follows the same logic. Okay. So I mean, the conclusion of our fairly robust experiment says that PCC is not a better idea than doing CC. Here in this table, I reported some of the data of these experiments. I don't show this because this is our experiments, but I'm showing this because it's a very robust experiment in which we tested, we sort of compared 13 different algorithms for quantification, among which some of the ones that I will mention from now on. And you can see that the data sets are very varied. Okay, so here there are 99 binary classes, here 88. And there are lots of test sets. I mean, so this generates more than 5,000 test sets with, and each test set on average is pretty big in itself, 15,000 documents. And the data sets represent a wide array of different class prevalences. So, I mean, we are here on RCD1, we are going from a minimum class prevalence of the positive class, which is 0. Okay, so in some data sets, there are simply no positive examples, and to a maximum of 0.53. And these also, I don't have values for drift here, but indeed, I mean, we have data sets in which there is a very, very high drift, okay? Very high discrepancy between original class prevalence and other data sets in which there is very low drift. Okay, so a very important method is adjusted classifying count. Okay, so it's also known as the confusion matrix model, and it's based on the observation that which is encoded by this formula. Let's try to read this formula. It says that the probability that a positive decision for class CJ is reached in the testing set breaks down into the sum of these probabilities. And the equation is pretty obvious, okay? So it's a direct application of conditional probability. So it's for each of the classes, we take the probability of the class in the test set times the conditional probability of the decision for J given that the class is the case, okay? So what are these conditional probabilities? These are essentially the misclassification probabilities, okay? So it's the probability that class J is assigned when class I should have been the case instead, okay? So of course, I mean, we take all of the documents whose true class is CJ and multiply by the probability that the label is misassigned. So instead of assigning the true class CJ, we assign C. Sorry, instead of assigning the true class CI, we assign class CJ instead. I mean, so this is a matter of fact. Okay. So essentially, yes.
If we have multiple classes.
Yes, we have multiple classes here.
So is that?
We have k different classes.
So the objective is where the test.
This is essentially the law of total probability, you know, which says that I mean, a probability of a certain event is the sum of the probabilities of that event conditioned on another event if these events are sort of a partition of the event space. So is this clear?
The previous experiment was binary or was probably below the classes?
The previous experiment? So these experiments we have run are binary, okay? But the methods, I will try to describe the methods in the general form for single label multi-class, okay? So when you have to exactly pick one class from several.
Just for the experiment that we started before this. So this was binary?
All of these data that you see are for the binary case. Yes. Yes?
How did you decide the cutoff points between the different events?
How do you?
How did you decide the cutoff points between the different events with very large drift and large drift? I mean,
how did we decide? I guess, I mean, that I should indicate, I should send you to the paper where we propose these experiments. But in terms of drift, I think that, I mean, we went by orders of magnitude. Okay, so drift was measured by KLD, which is natural measure to measure drift. And let's say we took very low drift was something which has something like has a an exponent of 4 or lower here or higher here. Low drift was 3, something like that. I mean, so we binned in a way which was not particularly smart. Okay, but it's. I mean, we didn't have any better way to actually. I mean, the thresholds were pretty arbitrary. Yes. So yes, to answer Alessandro, the experiments that you see here, I mean, the data I'm reporting, is we actually tested binary methods. But when trying to present the individual methods, I'm trying to present them in their general single label multi-class form, of which binary is a special example. Okay. So essentially here we have a simple instantiation of the law of total probability. And here the intuition is that, I mean, we have one factor here, which is something that the thing we want to estimate. Okay, so the probabilities of the class prevalences in the test set. So, I mean, if we are able to estimate the other two factors, okay, so we get this. So, I mean, the probability that a positive decision for class J in the test set is reached, I mean, we simply need to count. Okay, so we do have this. And these are the probabilities of misclassification. And the idea is that these probabilities of misclassification, we don't have them, but we could estimate them on the test, on the training set via k-fold cross-validation. Okay, so let's say since we have this, okay, and we have this essentially results in a system of linear equations where cardinality of C linear equations with the same number of unknowns. Okay, so essentially figuring out by this method the class prevalences, estimating the class prevalences, is essentially corresponds to solving this system of linear equations. Is this clear? I'll give you an example in the binary case, but yes, I'm taking the question here.
I'm just confused about the probability. Is that the positive probability? Is that the probability that class J is assigned?
This is the probability that class J is assigned. And here is the probability that class J is assigned when class I should have been assigned. So this is a misclassification. These kind of probabilities are the ones that you get from a confusion table. Okay. So I mean, if you basically do k-fold cross-validation, you can figure out all of these probabilities. Okay. So you can estimate these probabilities on the training set. Okay. So you don't have the real probabilities from the test set, but you have estimates from them. Okay. So you have this. You have this, and then, I mean, you can solve the system of linear equations to recover this. Yes?
Exactly my point was, if we are thinking of multiple classes that
Yes.
are binary classes, so they're point independent, so it's like it's the probability of assigning one. If it was an error, I would look at what was the classes that were supposed to be classified. Is that it?
Yes, it's a probability of misclassification. It's a probability of picking J when you should have picked I. Okay, yeah. And in the binary case, it comes down to the probability of picking the class when you shouldn't have had, to picking positive when you should have picked negative, and picking negative when you should have picked positive.
But that's what, for me, the confusion matrix, like when we have one label out of multiple classes. So I chose A,
well,
I should have chosen B.
The confusion matrix is a 2 times 2 matrix when you have binary classification. It's an n times n matrix when you have a single label multi-class, okay, where the ij entry means the frequency with which you have picked I instead of picking J.
But my point being, if I'm supposed to have two labels or more in the same example, how does that?
Oh, multi-label.
Yes.
Well, in that case, I mean, multi-label is always solved via binary. Okay, so this is the way we solve this I mean, all of these experiments here essentially is multi-label classification, but the standard way of solving multi-label classification is resorting to binary. Okay, so if I have 99 possible classes, okay, and each document can belong to 0, 1, or many classes, I solved 99 independent binary problems.
The confusion label is going to be just a 2 by 2.
So, I mean, when you solve multi-label, the confusion matrices will be 99 different 2 by 2 matrices, you know. So you will solve 99 different binary quantification problems independently, you know. And while if you do single label multi-class classification, so if you need to pick one of k, you will have a single matrix which is a k by k, you know. Okay. So I mean, in the binary case, I mean, the equation that we saw before comes down to this equation. Okay. So the probability of picking, say, D1, picking C1, so the positive class, is the probability of picking positive given that the real label was positive times the probability that the real label is positive, plus the probability of picking positive then given that we should have taken negative times the probability that the real label is negative, which is 1 minus the probability of positive. And the idea, essentially, I mean, this comes down to, I mean, algebraic manipulation means that the probability of our class, of the positive class, comes down to this equation. And of course, I mean, FPR here, what is FPR? It's the false positive rate for the test set. Okay, so it's essentially the number of false positives divided by the total number of negatives. Okay, so, and so I mean, the individual, I mean, when you have this notion of false positive rate and true positive rate, when you, all of these go down to binary, I mean, so you have a 2 per 2 matrix. Okay, so essentially, since we don't know the real false positive rate on the test set, we can estimate it, okay? And we use as an estimation the one that we have computed by a k-fold cross-validation, which is the false positive rate from the training set. So, I mean, this is essentially our so-called adjusted classifying count method, okay? Which is also known, goes also by the name of the confusion matrix method. And, I mean, this is a reasonably good method because it's one interesting fact is that you can apply it, as you have seen, to any supervised learning device because you take your regular SVMs, I mean, you do your regular classification, and then, I mean, after doing your regular classification, in order to compute a class estimate, you adjust, I mean, for your known tendency to err on the positive side rather than on the negative side or vice versa. And known doesn't mean known, but it means estimated, okay? Estimated by a k-fold cross-validation. Okay? So, I mean, what are the pros and cons? Okay? So the pros is that, I mean, ACC is known to return better, sorry, I should stand in front of the microphone, I guess. So ACC is known to return better class estimates than classifying count. And one slight problem is that, I mean, this method may also return values which are outside 0, 1, okay? Why is this so? I mean, because the probabilities of misclassification get estimated imperfectly, okay? So we have imperfect estimates of this, okay? So in this case, well, I mean, this requires a so-called clipping and rescaling, okay? So it means that, so if you have an estimated probability for a certain class that is below 0, well, you take it to be 0. If you have one which is above 1, you take it to be 1. So, and when you do these readjustments across all of the classes, which is called clipping, then they have to sum up to 1 again. Okay, so you have to rescale them. Okay. Well, I mean, doing this clipping and rescaling is really heuristic, okay? So it's not really reassuring, you know, that your method relies on this rule of thumbs, okay? And a second problem, which is even more, you know, troublesome, is that this method relies on the hypothesis that the misclassification probabilities can be reliably estimated on a training set. And this is a hypothesis which is a bit troublesome given that we assume we are in the presence of distribution drift, okay? So because we assume that the IID hypothesis is not really verified, okay? And so if it is not verified, why should be the misclassification probability is the same in the training set and the test set? You know, troublesome hypothesis, okay? So we really think that something better could be come up with. Yes?
If k equals 1, then this method comes down to...
If, say?
K equals 1. Let's
If,
say
k fold cross validation?
If k equals 1,
If k is equal to 1?
then does this method come down to the PCC method? Like that?
No, I mean, k fold cross validation is,
No, like
k stands for the number of,
yeah, if you do just one fold cross validation, that you don't do k fold cross validation, then can you show that this method is equivalent to the PCC method?
I think I haven't understood the question.
If you don't do k fold cross validation to estimate that one,
Oh, if you don't do any k-fold cross validation.
or just you estimate this from the whole training set, then
But you need, I mean, you need to have estimates of the false positive rate and true positive rates. Otherwise, I mean, this method,
no, I'm just saying that if you don't, let's say your k equals 1, so you have only one
k equals 1.
1. So you have only one fold on the training data.
One fold cross validation.
Yeah.
What's one fold cross validation?
It's just one, you just need your whole training data to estimate that one. Divide into k folds, you just use the whole training data to estimate this one. So then is this method same as previous method?
I think I'm confused. If you don't mind, I would like to take this question offline because I probably haven't understood what you mean. Anyway, okay, so we said that these assumptions that these misclassification probabilities can be estimated reliably is a bit troublesome. There is a fourth method here, which is called probabilistic adjusted classified count, and I guess you can get what it means. Okay? So it's essentially probabilistic adjusted classified count stands to adjusted classified count, which is the method we have just discussed, like probabilistic classified count stands to classified count. Okay? So it's essentially the same method we have seen, but for the fact that instead of taking misclassification probabilities, okay, binary data, we take the original, the expected value, computed from the original posterior probabilities. Okay? So, I mean, we don't, again, we use the notion, I mean, we use the intuition that we don't want to throw away all of the rich information which is present in the posterior probabilities, okay, which is something we throw away if we do thresholding, okay, if we, let's say, convert a probability into 0, 1 by applying threshold, okay. So we take expected values instead of counts, and by means of this, we actually expect to have rich information. But for the same, aside from this fact, I mean, we are still in the presence of a system of linear equations in which this is known, this can be estimated by a k-fold cross validation, and this is the unknowns that we want to figure out by solving a system of n linear equations into n unknowns. And where n is actually unknowns. I should say that is actually, this is not really n unknowns, but this is n minus 1 unknowns, because I mean, these are probabilities and they sum. Okay. So, again, I mean, the similar considerations apply as we have seen in the previous case. Okay. So again, I mean, George Foreman dismissed in principle, I mean, the very notion of doing PACC on the grounds that, I mean, also PACC relies on these posterior probabilities, and the posterior probabilities cannot be calibrated both for the training set and the test set at the same time if there is distribution data. Okay. Again, I mean, experiments of the people who proposed PACC, I mean, were positive, as you might imagine. I mean, so we try to submit to experiment of this again. Okay. So these experimentations were more varied. Okay. So while originally we had seen that PCC was inferior to CC, here PACC proved a good contender. Okay. So on these experiments, on the RC1 experiments, which are by far bigger than the ocean experiments, indeed PACC came out on top with respect to all the other methods that we have seen up to now. Okay, so I mean, we have up to now contrasting evidence on the fact that posterior probabilities are useful or not for quantification. Yes?
Can you just show better for PCC and PACC? So on one end you have expectation probability, the other probability. So here you have expectation over probability. The other question.
So here you have expectations. Okay, while in the previous equivalent method you didn't have expectations but you have counts. So I mean this essentially this is the probability that Cj, it's a fraction, okay, so it's a frequentistic probability. So it's you count the number of documents in which instead of choosing the CI as should have been the case, you mistakenly choose Cj. So this is a number of documents you count. Instead, I mean, in the other method, you basically sum up the posterior probabilities. Okay? So you come up with a figure that is the sum of all the posterior probabilities over all of the data set.
On the other end, you estimate both on the training data.
Yes, I mean, this is again an estimation of the training data.
So
it's again the result of cross validation.